Now, the waves that we've considered so far are disturbances that occur in a medium. The medium is the substance or material. Water is the medium for an ocean wave. The medium of a stadium wave is people. In a wave, the individual particles or components of the medium are only temporarily displaced. One particle's temporary displacement causes a nearby particle to temporarily displace, and so forth. The particles are not carried by the wave away from their natural position as they return to their original resting position over and over again. So this wave does not carry particle or medium away, or we say the wave does not transport the particles or the medium from one location to another. The wave only temporarily displaces the medium. One might argue that this is true based upon the following evidence. Despite all the waves in the ocean, there is still water in the middle of the ocean. The wave transports energy. Let's consider only one crest of a wave, or a pulse. The pulse is initiated by doing work or putting energy on one side of the medium. This energy is released to their neighboring particles to do work to displace them. This transfer of energy occurs over many particles, over a distance. If the transfer of energy between particles is efficient, the distance that the pulse travels can be very large. If the transfer of energy is not very efficient, say some of the energy is lost in friction, then the pulse does not propagate very far. The pulse transports energy from one side of the medium to the other. Now, you can think of a wave as a consecutive series of pulses, each carrying energy. A wave carries or transports energy. A wave that transfers energy through the displacement of the medium that it passes through is called a mechanical wave. The idealized waves that we've explored are transverse mechanical waves. Transverse because the medium is displaced perpendicular or transverse to the direction of the wave, and mechanical because the wave is a mechanical disturbance of the medium. Now, a striking example of water waves carrying energy is the 2004 Boxing Day Tsunami that killed between 240 and 280,000 people living near the coast of the Indian Ocean. The initial disturbance was an undersea earthquake with a significant vertical displacement of the seabed. This earthquake released an immense amount of energy, the equivalent of roughly 26 megatons of TNT, and this energy was transported by the waves over far distances. Now, in deep ocean water, the tsunami waves form only a small bump, barely noticeable, but those waves travel at very high speeds of between 500 and 1,000 kilometers per hour. Radar satellites recorded heights of these small waves in deep ocean of only about 60 centimeters or 2 feet, some 2 hours after the initial earthquake. But in shallow water, near coastlines, that wave slows down to only tens of kilometers per hour. But in doing so, it forms large destructive waves. Scientists investigating the damage in Aceh found evidence that the wave reached a height of 24 to 30 meters. That's in excess of 100 feet. A lot of the energy released by the earthquake was dissipated or used in traveling across the Indian Ocean, but a whopping 20% of the earthquake's energy, the equivalent of roughly 5 megatons of TNT, was unleashed by the tsunami waves crashing onto the coast surrounding the Indian Ocean. Hence, the undersea earthquake's destructive energy was transported to the coastlines of the Indian Ocean by waves. Slinkies make great demos of transverse mechanical waves. You can generate a transverse wave by displacing one end of the slinky. A single pulse is generated by displacing your hand up and down. Notice that the up-down pulse travels from left to right. Notice that any particular coil in the slinky goes up and down, but the wave travels from left to right. That is, the medium, the spring, oscillates perpendicular to the direction or propagation of the wave. Also note that to generate a pulse, the person puts energy into the slinky or does work to displace the slinky end in his hand. That energy is transferred progressively along the slinky to displace it and is used in displacing the other end of the slinky. So, no matter has been transported down the length of the spring, but energy has been transferred down the length of the spring. Hey, you can create another type of mechanical wave with a slinky. Look at this. Here, a single pulse is generated by displacing one end right and left. Notice that the left pulse causes a compression of the spring, which travels from left to right. Notice that any particular coil in the slinky goes right and left. The medium, the spring, oscillates parallel to the direction or propagation of the wave. Again, to generate the pulse, the person puts energy into the slinky or does work to displace the slinky end in his hand. The energy is transferred progressively along the slinky to displace it. And at the end of the slinky, some distance from the person's hand, the energy is expended in displacing the opposite end. Again, no matter has been transported down the length of the spring, but energy has been transferred down the length of the slinky. The compressive waves of a slinky spring are longitudinal mechanical waves. Longitudinal because parts of the spring are displaced parallel or longitudinal to the direction of the waves, and mechanical because the wave is a mechanical disturbance of the spring. Let's look at this a little more closely, considering the motion of only a few points on the spring, uniformly or evenly spaced on the spring at rest. When we introduce a compressive pulse, you see that some of the points are brought closer together or compressed, but their position and spacing is restored with the compression traveling down the line. The points only oscillate about their resting position in the direction of the wave. They do not travel with the wave. You can see this by following the blue point. Now let me add consecutive pulses. If I freeze the simulation, you see regions of compression where the points are closer together, and regions of rarefaction where the points are farther apart. In the compressed regions, the slinky spring force pushes the points away to restore their spacing. In the rarefied regions, the slinky spring force pulls to restore uniform spacing. And if we plot the local force as a function of distance for a time-frozen slinky, we can recognize characteristics of a wave. The wavelength is the distance between consecutive compressive regions or consecutive rarefied regions. The amplitude is half the distance between the maximum compressive and maximum rarefaction forces. Unfreeze the spring, and we see that the time that it takes for a compressive region to travel one wavelength is the period. The frequency is 1 on the period, and the speed of the wave is the wavelength divided by the period. Now, you experience longitudinal waves every day, including at this moment as you are listening to the video. When sound travels, air molecules form a series of compressions and rarefactions, as shown in this sound wave, frozen in time. At compression, the air pressure is higher than normal, and at rarefaction, the pressure is lower than normal. So here's a plot of the air pressure versus distance. We can easily recognize this as a wave. It looks like the displacement versus distance curve of a transverse wave. And because of that, some may forget that the sound wave is a longitudinal wave, not a transverse wave. Don't forget the difference. Sound waves are longitudinal waves. Sound waves are not transverse waves. Next time, we'll explore how we measure these sound waves and how we hear and generate sound.